First, like always, let us do a quick review of the lecture 6. And there primarily we discuss about design space exploration. And then we have this different implementation of basic building blocks, and we saw the implementation of an adder. And then we learned about how to automatically test our design. And today we will, and then we spend little time in doing design space exploration. Today we will try to do some hands-on work on how to use generative AI assisted code generation. And then there are two different types of architecture which I want us to study. One is a dedicated fully parallel architecture, which perhaps is the easiest architecture to design. As in this case, all you do is that you just, whatever algorithm you have, like we did with the sorting algorithm, that you just lay the complete algorithm out, open all the loops and see where there is an addition, you put an adder, where there is subtraction, you put a subtractor. And so you have this whole thing, and you create an architecture. But more intricate architecture is once you have time shared architecture. And so we will go learn about system level architecture design, the main design decision, that whether out of, so I would say that there are three different types of architecture. Okay. One is fully dedicated. So this perhaps is easiest to design architecture because fully dedicated means that for every operation in the algorithm, you put a hardware resource, an operator. The other one is time shared, because you have many clock cycles available to you. So you don't want to just do the work in few clock cycles, then wait for the rest of your life to do the next iteration, okay? And we will see an example then when to use a time shared. The third, which is very interesting, is where you need to do a lot more than what is there in the algorithm, okay? So this is where you got to exploit parallelism. So you want to run your hardware 10 times faster than the clock rate, for example. Let's say you have a clock rate of 100 megahertz and you want to run an architecture processing 400 mega samples per second, which is like 4 times at a higher speed than your sampling rate. And why this has become very important? Because of the internet speed. The internet is now going from some megabit to terabit, gigabit, and now easily you find interfaces which can bring 400 gigabits of data into a system, 400 gigabit. So somebody has to process this amount of data, and there is no way that you can run your clock at 400 gigahertz, okay? So it means that there is something which is happening faster than the circuit at which you can clock. So you got to do a lot of things in parallel. So that is another extreme architecture where you have to exploit, and it is becoming more and more important because of all these large language models, generative AI, where people want to process as much data as possible in the hardware. So we are going to just move in this in the spectrum, moving from fully dedicated to time shared to what all parallelism can be exploited to even do better. A review is that we have already covered that the tail has to be a wire or a edge, and head has to be a wire, and this is how you can just connect modules together. This was very important, that because a lot of work has to be in the verification. And in verification, important is that how you put a simulator in your design, and you generate all kinds of test vectors. So there's a lot of creativity in developing the test bench, and especially how you kind of generate a test vector that can give you a maximum coverage of your design. A coverage means that you basically ideally switch every transistor from 0 to 1, and in relation to one transistor, a combination with the other, like this 0 to 1, then this 1 to 0, and this also. So if you start making all the combination and permutation, it is not possible actually, even to design a 232-bit adders, just a 32-bit adder, adding 32-bit numbers. Because you start generating all possible 32-bit numbers, it will be 10 raised to the power, 2 raised to the power 32, and then another 2 raised to the power 32. And so many input, and just checking an adder. And now imagine if you have 1 trillion transistors. So it's not possible. So that's why verification is becoming more and more challenging. And so you got to be very creative. And this is the minimum that you can do, that there is a simulator which you believe that works, and giving your test vector to both the simulator and your RTL code, and automatically checking and then automatically logging. So the UVM kind of gives you the same kind of framework, where it has all the elements, where you have the driver, the sequencer, putting your test vectors, and then getting your test vector back, having a monitor, having a scoreboard. Okay, so doing all of this for you. So there is a framework, but you can, if you, one is that all these generative AI tool will also generate you a UVM framework as well. So we will try generating a UVM framework for some design and see that, yeah, it works. And the other one is that UVM kind of a framework, where you have a simulator already embedded into your verification code, and you are testing the code. So this is where, because of the importance of everything what I have mentioned, there is a framework. And as I mentioned earlier, there is also a course, a semester level course, where they are learning more about UVM. But I know for sure that you can just generate this UVM code. I've generated it myself, and you generate that code, or UVM test bench, and then just plug in your design specific information into UVM to make it work. So we will do that at some part of the course. And this is also very interesting, and this is from the latest conference that happened in California, and how EDA, the generative AI, is helping EDA designer to explore the entire design space. It was not possible previously to have multiple RTL implementation of a complex design and do this exploration, but now it is possible, because you can just generate a code. So you can have multiple RTL implementations, and in the design space, where you got to make sure that you find the sweetest spot which gives you the best trade-off between how fast you want to clock it, how much power budget you have, how much area you want to consume. So under all these design constraints, you got to fit yourself at the best place. Okay? And that best place is not very easy to figure out, because once you find out where you actually sits in this design space, you are away from RTL. So there is an RTL design, then you got to synthesize it, then you do place and route, and only then you will find out that how fast can you clock your circuit. So means that all these generative AI tools which have these agents, that they are keep taking your RTL and passing it to the layout and the synthesis tools, and giving you an estimate of where you stand in this trade-off, so that you find your place, the best place where you should be. Because there are so many different options of every design element that you put in hardware. I gave you an example of simple an adder. Adder has so many ways to actually implement in hardware. So many, and people are still exploring. I have seen PhD theses which are still working on multipliers, for example. Okay, so you get amazed that people are still figuring out ways of multiplying numbers. And we only know you generate partial products, then you add them together. But there are so many different ways of even multiplying numbers. So people are spending still a lot of time in finding out that how better, because adders multiplication is very core to most of the algorithms that you do. And usually this is the trade-off, that you try to improve one, so you have to lose the other. Okay, there is no way that, provided that you are doing everything the best. If you are a dumb programmer, definitely you can do bad. But if you are a very good programmer, then you got to be ready for the trade-off, that this is the trade-off that you are kind of going to have. So this is frequency, power, and area trade-off. We said this is how you are just moving in this space, finding out the very best that you can do, and figuring out whether power is important. You say, oh, power is very important in my case, and because it's a handheld device. So power is important means that you got to make sure that your design caters for that. It can run your battery for hours, so you got to slow down your clock. This is the one option, at least, that you slow down your clock. Okay. So we check about adders, and we said there are some embedded adders in FPGAs, like in Versal, you have this DSP58, and then we said you can just ask the generative tool how many different adders that you can have. I'll just give you a list of adders, and you say, okay, generate me, for example, this is a carry select adder. And this code, believe me, it's so compact and so nicely written. It otherwise takes a good programmer many weeks to write such a good code, okay? Because it's a two-dimensional arrays it is using, and it's not an easy job to write a code for something, a carry select adder. So, but it has just generated that code for you. And then is more interesting is the way it has generated the test bench, okay? So again, it is doing something nasty, but let's not. So here is the self-checking tests, and this is kind of the golden rule that we are going to have to do the test. You must able to have a model, and in this case, model is very simple, but usually the model will be very complex. It may be your Python implementation. So you have a Python implementation, you do the Python implementation, take it to generate all from the test vector, generate all the outputs, then give the same test vectors, and one by one keep, either you read it from a file that these are the answers, and if you are doing white box testing, it even becomes more intricate, because in white box testing, one is black box. Black box is you give input, you get an output, like we are studying SHA 256, okay? You give input, you get an output. So you generate, you give a lot of inputs, generate a lot of outputs, you put this in a file, you put this in a file, okay? And then read both the files in your stimulus and start generating. So the sequencer start generating sequence by sequence all the inputs that you have given to SHA 256, and from the other file keep getting the answer as well. And you believe that what you have in Python is actually the correct code, and then just keep on seeing whether you are getting the right answer or not. But if you want to go inside the design while you are thinking that no, I don't want to do just the black box testing, so I have tested all the pieces of the puzzles, all the pieces in the design, but I still want to have some intermediate values, okay? For example, you say, I want, after first iteration, what happens? What is the value of A in my SHA 256? So you also have to dump that into this file. If you're doing a white box testing, find out what all you want to monitor, which is inside your module. And all those variables are also there in your Python code. So once you're dumping your results into a file, whatever you think is important. So think critically, I think this value will help, this value will help, this value will help, and also bring, because you are doing automatic testing, you are not really humanly testing it. So if you're very creative, figuring out that you're not missing anything, that once a bug happens, you want to precisely know that this is something which is not working, okay? So then you have to have something inside. So we say white box testing, where you got to know the design. So only a designer can do white box testing. If you expect a verification engineer to do white box, it will be very difficult for him, because he does not really understand the intricacies of the design. But as you know the intricacies, you say, I know what all I have to basically do. So you do that, and that will help you to primarily help you to do the white box testing. So this is the result which I showed you last time, self-checking test bench, and interesting is the corner cases. So always, again, usually corner cases are important, because no matter all the test vectors you are generating randomly, so it may never generate a test vector, a corner case, okay? So as a designer, you need to understand that this is the corner case which checks the extreme of your design, that this is your extreme of my design. Usually it is saying all zeros, all F, all 1, 1, 1, 1, 1. So, but it will change, like what is the, your corner case would change. So people must know the corner cases to make sure that you are first how to randomly generate the test vectors and then how to check the corner cases. And then we started learning about LLM only from the perspective that you need to know how the large language model works, so that once you're giving a prompt, you should have this basic understanding. And there I told you that it has a context window, and context window is where it will vectorize every word into a vector, and then we'll try to understand the meaning of every word in the context window to have a complete understanding of whatever you have typed. And it is chain of thought prompting, so whatever answer it gives, it also put it in the context window. So you can ask a question which relates to your previous prompts, so previous to previous prompts as well. So this is something important, that learning about that it tokenizes everything that you write, converts them into vectors. So every word, for example, for llama, every word is a 4096 element vector. Okay, so it's not like only a 3-dimensional vector space. I showed you that how the dictionary basically moves in a 3 dimension, and how it finds out the which we say self-attention, a word, how it relates to the other words in the context window, right? So it somehow figures out a relationship of every word with respect to the other word, and it tries to understand the context of whatever you have typed in this window. For example, swam relates to the river and also to the bank, but then there is another relationship where swam also relates to who swam, I swam. Okay, so for every word there is some relationship with the other words. So this multi-head attention would make sure that the relationship of every word with every other word is understood by this engine, and that's how it just creates a self-attention matrix, and then it creates all the weights, and then it multiplies all these vectors with all these weights. Now this y2 is very different than v2. v2 was I swam, it was just a word swam, so it does not know what other words were there. Now y2 understands swam, which is this v2, but also it now has some portion of v1, some portion of v2, some portion of v3 weighted by the self-attention. So now y2 has a very different character. I cannot find a word in English which can describe 10 words in English, okay? But I can find a vector in maths which can actually have meaning of 10 words in maths. This is what it has done actually. It has now meanings of other things in relation to itself, okay? And that's what all the large language models are doing. That once it goes down and finding out all the weights and then changing themselves according to v2, v3, v4, v5, v6, every word in the context window, okay? Obviously, you cannot have an infinite dimension context window because a lot of computation that are happening because of the context, the size of the context, and it used to be very small. Now they are increasing the context window size, because the first word you write in the context window to the last word is written in the context window. They all got to be related to each other somehow. That's a lot of work that the LLM has to do. That's why they require a lot of computational power as well, because of doing all these correlations and stuff. So, but important is whatever you write in the context window, it has some meaning in relation to the other words in the context window, okay? And then they have the training based on what type of vectors they are there. So it will try to steer and get the weights in a manner that learn from the entire internet, that how once these are the contexts, what word should it generate next, what word should it generate next, right? So these are the parameters which we call a large language model. We say it is a trillion parameter or 1 billion parameter or 7 billion parameters. So these are the weights which you first take the vector, convert them into another vector, which are now you are multiplying a vector with all these matrices, which are the weights, and then doing the same thing, finding out another set of the same dimension set of vectors and taking it from one layer to another layer to another layer to another layer and getting out of these layers finally. So this is what I was trying to explain, that SWAM has a relationship with the river and the bank, but then it has a relationship with I as well, because I swam. Okay, so that's what it is trying to figure out, and nobody really understands that how could actually it figures out so much, but it works. So that's what fascinates people, that it works, and this is kind of a multi-head attention where every word has different perspective. Okay, swam has different perspective once it comes to river and swim. Swam has different perspective, that who swims, I swam. So it would figure out every context of every word in the context window, I guess. So, and how it could actually able to capture that because of the size of the vector, because this is a big vector. Now word is not a word, it is a vector. So it can have color of everything in the context window. So every vector gets color of everything in the context window. So this is interesting that you are primarily doing this. So for example, swing the bat and the bat flew at night. Both are bats, but I'll just figure out that, and because of the same thing, that attention mechanism would help. John does not eat meat. Pete does not like steak. Who is vegetarian will figure out who is vegetarian, because every word is related to every word. So it is not, otherwise once you are typing, it will only see the previous word and will start suggesting you the next word, and usually it is incorrect what it is suggesting when you are typing on your WhatsApp. But here the context window is very big, so it can never go wrong. Mostly it will never go wrong. As for example, the doctor asked the nurse a question, she said, so it means nurse said. But the doctor asked the question and he asked, so it means doctor asked. So it'll have, no matter how previous in the window something happens, it will still able to figure out that this actually relates to that because of all those positional encoding, and So I'll not get into, because it's not a class on large language models, but still just this is more than enough for us to understand from the context of EDA tools, that whatever is in the context window, every word in that window relates to every other word in the context window. So it has very good understanding of the context. So every word gets color of every other word in the context window, to say, which is honestly very difficult for somebody to perceive, that how can a word has kind of meaning of every other word in a book, for example, but it has. So that's what the beauty of the LLMs are. Then there is other thing which people are using in EDAs and in other also application is RAG, retrieval augmented generation. And here what people do is that they put already generated content which is not on the internet. So LLM are using everything which is on the internet, but then you have yourself developed Verilog code for so many things for last many years, and that's what big companies are doing, that all the code that they have developed, they are putting it in RAG, and once you put it in RAG, so then it basically what it does is that it vectorizes the content. So it basically divide it into chunks and put it into convert them into vector database. And once you ask a query, and it'll go find out the relevant portion, and then it'll just bring that out, and usually it passes it to an LLM to just change the language, or to just combine them together and give you an answer. So RAG models are important. So this is again I have taken from that this is how the people are perceiving from a conference which just happened, that what all people are trying to do. Okay, so there is proposed RTL for the following specification. It can do that. They're using RAG to ask a specific question about the IP that you already have generated. And then it's not only that, they are using multi-agent system to generate RTL code, then say you simulate it, then you synthesize it, then find out there is any synthesis related error, and then you come back. So they are just making this a gentle approach where there are multiple agents, and they are just automating and doing all the by itself, exploring all the possibilities instead of a human actually doing all the work. And then even doing the management part, email me whenever a new bug is found. So it says, okay, keep doing this, keep doing this. If you find a bug, tell me that this is a bug, so that you can then go and find out why there is a bug. So this is where like people are moving, and behavioral adoption always use, and you can tell it. Somebody also pointed out in the class that I want to use neg edge reset, for example. So you can give these kind of instruction as well to. So this is the multi-agent workflow automation where you already have an IP, intellectual property भी है आपकी, then you have, and then you write, you have a RAG model, then you have LLM, and they believe that you can get, so you ask it, so this is a task dispatcher, is doing the design, it is doing generating the test bench, it is generating all the results, doing the regression analysis, checking the coverage, and saying 99.2% coverage means that the test bench has done good coverage, and also putting it on the GitHub, and so that it's also doing the management. So, and there is a project repository. So this is what people are trying to do in EDA, that they're trying to automate every aspect of design, testing, and managing. So everything, so that the agents can do most of the work. So LLM plus RAG, so this is what the EDA is going to look like. So let's now try to generate, and if you have like laptop है लोगों के पास, किसके सबके पास है कुछ है, let's I want you to do this exercise yourself. I tried it myself, so I could actually, so what I did was मैंने उसको चैट जीपीटी पे कर लें आप उसे कहें कि आपको if you go on chat GPT and ask chat GPT to generate, अभी हम SHA-256 कर रहे हैं, लेकिन फिर मैंने जाके उसका एक CNN को भी किया था, generate SHA-256 code in detail without using, generate code, Python code for SHA-256 without using any function, ठीक है? So all you want is that ChatGPT should generate the SHA-256 code, and it should not be using any function. It must not say SHA-256 and see if I can. So this is chat. Generate Python code. अच्छा, code for hash-256 without using any function. तो ये सारा इसने कोड जनरेट कर दिया है, नजर आ रहा है आपको? Okay, so it has actually generated all the code with all the constants and everything. एक मिनट इसका ठीक है जी. Can you see this? अच्छा, अब अगर आप देखें, so this part is the main combinational logic in the loop. So it's using a right rotate function and then and XOR इस तरह कर रहा है, right rotate function है, and it is doing some other more operations and then doing this G to H, F to G, E to F, and then actually doing E, going this C to D, B to C, A to B, and this, and then it is updating ये सारा कर. So it is using a right rotate function, and go to the right rotate function, and here is the right rotate function that it takes bits and then it is just shifting them to the right and shifting them to the left again and then ORing them so that you get a अच्छा, अभी what I want to here emphasize that once we are generating RTL Verilog code, there are two parts to the code. One is the combinational logic, the other one is the sequential logic. Combinational logic is exactly what is here in the Python code mostly. Once you say Python not to use a function and generate the code, so that is all is your combinational logic. Okay. अब इसने एक function है rotate right वाला जो इसने खुद से उसकी line भी लिखी हुई है. So what I do is I copy this function and I copy it and then I go to ChatGPT and I say generate RTL Verilog code for right rotate as is done in Python. And now remember, it has a context window. In the context window, the Python code is already there. Okay. So आप इसे कहें जैसे आपने Python में किया ना, मुझे ये अब इसको RTL Verilog में करना है. इसका टेस्ट बेंच भी लिख दिया. So here is the right rotate function, device under test. अच्छा ऊपर होगा. This is the right rotate function. Right? Very simple. What it has done is now, but it has created a module for right rotate. Okay, it's a module for right rotate. And you say नहीं यार मुझे function चाहिए. I want right rotate to be a Verilog function rather than a module. Okay, so it's generating. टेस्ट हो रहा है. अब इसने इसका फंक्शन बना दिया. ठीक है. सो ओनली इफ यू अंडरस्टैंड a little bit, at least enough of Verilog that you can ask and remember the context window concept, that everything is getting into the context. So it understand, अच्छा मैंने तो ये मॉड्यूल लिखा हुआ था, अभी now you wanted to write a function. So because it understand the context and actually it has actually written module, कोई इंसान तो नहीं बैठा हुआ. How the all the self retention mechanism, कि उसने कोरिलेशंस किए हुए हैं, मॉड्यूल फंक्शंस ये वो. सो इट विल फिगर आउट. अब ये जो आपने लिखा है ये भी सारा इट इज़ गोइंग एज अ कॉन्टेक्स्ट टू इट एंड अगेन फाइंडिंग आउट कोरिलेशंस ऑफ एवरीथिंग विद एवरीथिंग एंड मेकिंग सेंस व्हाट यू आर ट्राइंग टू आस्क. I'll just do this. Now so now this is very good that it has actually generated a function. Now you go and you copy this अच्छा इसका मेरी इसने कॉन्टेक्स्ट आई थिंक इट इज ओके. सो what I do now is, and which is important for us to understand, कि ये सारा कोड है जी, ठीक है, ये इसका मेन लूप है. ओके, नाउ आई कॉपी दिस, मैं इसको कॉपी करता हूँ यहाँ से, ये मेरा मेन. ओके, और अब बिकॉज नाउ व्हाट आई वांट, आई डोंट वांट टू बेसिकली, बिकॉज this ChatGPT has little learning on Verilog and a lot more learning on Python. Python के ऊपर it's proven that it is almost 99% accurate most of the time. Okay, so it's very strong learning on Python, and because Verilog का इतना ज़्यादा code base नहीं है, तो it would still do some errors, mistakes in while if you just ask it to generate Verilog code, because then it'll go and it'll try to generate the Verilog code. But now what you do is that this is the right functionality and you can test it, check it. Now you just copy this functionality in your context window. Say, take this Python code, okay, now generate me a module which is part of a SHA-2 do it yourself. Okay, copy this code. Okay, now you have already written a function which is a write rotate function. वो आपने लिख लिया था. You have already written a function which is the write rotate function. अब आप उसे कहें जी use the function this generated write rotate function, and remember context बना हुआ है आपका, अभी context window में ही चल रहे हैं अभी तक आप. तो use the function and the code which you just generated in Python to write a module in Verilog which should take K and W as input, K and W as input, ठीक है, and update the values of all A, B, C, D, E, F, G, H register, and at reset should initialize, and no matter how you can write, because remember ये जो context window है बहुत बड़ी है, ये सारा context window में पड़ा हुआ है. So while writing a prompt you don't need to be miser, you don't say कि मैं तो पता नहीं ज़्यादा लिख दूंगा तो क्या हो जाएगा. Write whatever you want to write. That is important. Write whatever you want to write, because the context window is pretty big. So and you can exactly figure out कि ChatGPT की context window कितनी है, Gemini की कितनी है, इसकी कितनी है. So whatever you write in the context window, make use of the large window size that they are giving you. So copy this, tell it that once it initializes, initialize it with the initial values of h है, k है, h है, जो भी शुरू के variables हैं, k है नहीं h है, जो initial variables हैं h. हाँ, so at reset initialize A, B, C, D, E, F, G, H register with values of h. Otherwise on every clock update A, B, C, D, E, F, G, H, all these registers with the following logic that you have generated in the Python code. तो उसको आप कहें आपने सारी लॉजिक को Python कोड से लेकर इसका Verilog कोड जनरेट करना है. So let me do that for you also. So I say now generate RTL Verilog code for the designing of SHA-256 algorithm. On reset, set all the registers A, B, C, D, E, F, G, H to constants H, and then with every clock cycle update the logic as given below, where K and H and W are two 32-bit input along with clock and reset, and you copy it here. चलना शुरू हो गया, सही है. So this is how is just generating the code. सही है, बहुत ही परफेक्ट किस्म का ना इसने कोड जनरेट किया. लेट अस जस्ट सी दिस कोड. सो हियर इज द कोड वेयर इट हैज द लाइक at reset, so it has this at the reset it is just ये सारे constants हैं उसके. सो रीसेट के ऊपर अपडेट द रजिस्टर. इसने उस लॉजिक को तो सही एग्जैक्टली वो कर दिया यहाँ पे, ठीक है. थोड़ा सा अभी भी इसको आप देन यू हैव टू talk to it again. On reset, the registers A be initialized with H with 8 32-bit constants of H, and in every other clock cycle they should be. उस ये पार्ट उसने सही किया, थोड़ा सा उसको अपडेटेड with computed values of A, B, C, D, E, F, G and H based on the logic generated in Python code and is copied here. जब मैं उसको लॉजिक को ये आगे जी, ये H कांस्टेंट है. ओहो, ये आता. Oh, okay. Let us see what it generates now. So इसने सारा लॉजिक बिल्कुल ठीक करके जनरेट किया है. इट हैज़ काइंड ऑफ कॉन्स्टेंट्स को भी रीसेट पे इसने, लेकिन कॉन्स्टेंट को साइन करके, ये ABCD को साइन करके, और ये सारा लॉजिक इसने सही डाला हुआ है, और फिर ये भी सही किया हुआ है सारा. और ये बाकी का कोड भी ना वो कर रहा है, जहाँ पे H के ऊपर दोबारा असाइनमेंट होती है और H के ऊपर ये सारी वैल्यूज़ रखता है. सो मीन्स दैट यू can primarily use the logic that it has generated in the Python code, especially the combination logic, and then you can copy that to your the Verilog code. So एक आदि और मैंने example की थी, I'll show you that too. So so ये वही सारा, ये मैंने जो खुद से generate किया हुआ था, ये मैंने I generated a function, then I asked it to strategies, I asked it to generate a function rather than a module. It did that. Then I wrote this prompt myself कि जी इसको पकड़ के आप उसमें डालें, तो इसने उसको भी बहुत आराम से कर लिया था. So now I would like to discuss the type of architectures that we can design. Usually all the architectures are governed with the sampling data, at what rate all the real-time systems. So our interest is mostly real-time systems. As I mentioned, the networking systems, now they have the interface of 100 gigabit per second. This 4G, 5G are again have very high data rate requirement. Like they are, if they are doing 64 megabit per second, then 64 megabit into number of samples, that for every bit how many samples you got to have. So most of these systems are basically constrained by the rate at which you have to process data. Okay, so that is something very important. And usually we first, let's say we call this f of s. F of s is the rate at which the data is coming to your system. Okay, if it is a high definition TV, for example, HD TV, so you have, let's say, 30 frames every second, and every frame has RGB3, and then it has so many million pixels. So you got to figure out that at what rate you have to process every pixel, and that would give you from the architecture perspective, the biggest budget is the rate at which you have to process data. That is number one. Okay, so this is usually, it depends upon that what type of application that you are implementing. FS is important, the sampling rate or the data rate at which you have to process if you are real time or near real time. The second important thing is that you are designing a synchronous digital hardware. So our focus is only on synchronous digital hardware. A synchronous digital hardware means that there is a clock at which you are running your circuit. So a synchronous digital hardware has a clock. Okay, so we are not, nobody does asynchronous circuits, so everybody does the synchronous circuit. So it becomes, the design becomes very simple, the synthesis becomes very simple, your targets become very simple, that you always have a target clock in mind, that I am going to clock this at, let's say, 500 megahertz. So you set a target for yourself. So that is the target which is given to you, that you are planning to run this device at a certain clock. We usually call this F clock. Okay, so these are the two major design parameters that you have, that at what rate you have to process your data and at what clock you are targeting to run your circuit. So your design would always look like this, where you have registers or memory, storage, and because it is a synchronous circuit, so you got to break all the logic as an architect into cloud and register, into cloud and register, into cloud and register. Okay, and I was saying this cloud, if you are thinking about your design in this manner, the cloud you can first design in Python, the functionality where actually things are happening, and then you can copy that functionality into your RTL Verilog code. Either you can ask the and you should plan your design in this fashion, that there is a functionality, then there is a storage, then there is a functionality, then there is a storage, then there is a functionality, then there is a storage. So always your design should be as a synchronous digital logic, where the functionality is broken down into smaller clouds and registers, and the slowest path in this would determine your clock rate. Okay, the slowest path. Let's say there are billions of paths, but there is one path which is not running at 500 megahertz, means you cannot run that chip on 500 megahertz. So this is the biggest challenge for chip designer, that the slowest path governs that how fast you can run the chip. And that may be just one path, and that is something you are always trying to find out the slowest path and trying to speed it up. But it is better that while you are designing, that should be in your mind, that there must not be a slowest path in your design which constrains your design. Because otherwise sometimes making that path faster becomes very, very challenging. You cannot just go, because everything is so synchronous, everything is happening on the beat of a clock. So beat of a clock. Okay? You cannot just add another register because something which you, for example, something which you calculated here, okay, is related to something which is here and something which is here. You cannot just go and put another register in between the cloud, because it will just change the synchronization of the whole thing, because then this will be sending the previous value, not the current value what you are computing. Okay, so a register is also a delay, a one cycle delay. Anything once there is a register, it means you are holding on the next computation one by one cycle. And so there is a previous value, then there is a new value. So a register means a delay as well. So, but this is how a synchronous digital logic would look like. Okay? So you may have 1D data coming into your system. So you have just very simple way of figuring out that what is the rate. It is just the sampling rate. You may have a 2D data coming out, mostly all these CNN systems where you are using deep neural networks on videos. They have 2D data. If it is color, then you have RGB as well, and then resolution of the image, and that will determine that how fast you have to process. And you may have 3D data coming into your system, which primarily is the videos that you have to process. For example, in communication system, you would see you are designing a communication system where you are converting it into digital data, then you are down converting, then you are demodulating, then you are doing error correction, then you are doing source decoding if voice is compressed or video is compressed, and then you are playing it on the mic. Every kind of a system looks like this. These type of systems even become more challenging, because as you are moving down the receiver path, your data rate is also changing. So it is not the sampling rate, which here once you are playing it on a mic, it is only 8 kilohertz. But once you are sampling, it may be 500 megahertz. So now you can see the difference, like something which you sample at 500 megahertz will actually be played at 8 kilohertz. So it becomes again a big architectural challenge to handle variability of the data rate throughout your architecture, because once you are, and same thing happens in all neural networks as well, that once you start, you have just an image comes in, so it has a resolution, and then you, through CNN, you expand it, you make, like you have kernel which has like 64 kernels, and you expand it and expand it and expand it, and then finally you converge and you have only one decision to make, whether it is this or that. So the data would go like this, and then it will go like this, and all this variability in real timeness, you got to figure out that this module will get data at this rate. And another challenge that comes in is that sometimes you are not processing all the data at the same time, like sample by sample processing is not there. For example, once you are doing forward error correction, so usually these are block codes. So for example, you need to have 212 bits to figure out if there is any error in the, so there is a frame. All the IP network, there is a frame. So but once you give it to the source encoder may require 520 bits to do the decoding, because it is voice compression or video compression. Okay, so means not only the data rate is changing, but the amount of information that is required to kick on the next block is also changing. And so you cannot run this 520 if you have only 212 bits coming out. So even you cannot kick it once you have 2 of these you have processed, and you can only do it if you have 3 of this. And but then you have some bits left to be processed in the next iteration. So it becomes, the problem start becoming very, very complex, And usually this is what, once you are designing an architecture, this is very typical what an architect should be worried about, that you have not only the sampling rate which is varying, but the amount of information which you process by every block, that is changing. And it is not exact multiple of the others usually. Okay, it is not that you have 8 samples here, then you have 4 samples, then you have 2 samples. Sometimes there is no common factor that you have to cater if you are doing real time. So the system level architecture becomes a complex thing to design, that we are not really worrying about, and it is real time also. So you don't want to miss any, you don't want to create a latency that you cannot say, oh, first I will collect 20 of these and then I'll process this, then you will add latency into the system. So the best system is that as soon as you get enough data, you kick the next block. Okay? As soon as you get the data, you kick the next block. This is the best system. So there is this concept of firing, that you have enough tokens. So there is a concept of token, that you are collecting tokens, and whenever you have enough tokens, you fire the next block. Okay, you say, okay, next block, you start processing. The simplest design is that at the start you collect tokens, and tokens are nothing but number of samples that are input from one block. So whenever you have enough token, you fire this node. You fire the node, and then as the result of firing, you generate more tokens here, output pay. Now you have these tokens, you fire this, and you have more tokens. But what becomes challenging is that because you are designing an architecture, okay? So the firing is not happening at regular interval in time. Sometimes you are waiting to generate the result, as I mentioned earlier, that you have, let's say, for example, you have 225 samples coming out of FEC. 225 coming out of FEC, but this will only run on 556 samples, the next block. So if I make it like, so you have this block, then you have this block. So this generates 225, but this requires 556. So you do it twice, you get 550. Still you don't have 6. So this guy is just waiting. And then you get another 225, and you say, okay, you start. But then it gets another 225 while it is doing its work, and now it already is carrying 200 samples. So it will have 400 something samples, and then next time something comes and it'll just kick this block. So once you see that at what time it executes, that time is changing on the timeline. Okay, it is working now, waiting, working, waiting, working, and figuring out that how fast should you make it execute. It becomes little difficult. Okay, because it's not working all the time. It's not single. So either you say no, I want everything to work all the time. Becomes very challenging problem to again solve at a system level. Once you are an architect, you are designing a system level architecture. So an easiest approach is that you make the slowest figure out that how much little time you will get to execute in real time, and design according to that every block, because every block, every node has to be designed differently. And then this is something which is called Kahn Process Network, that all the inputs you put in FIFOs, so you are generating, you put them in the FIFOs. Okay, so FIFOs are like first in, first out. So if you have a requirement of 556, so first you generate 225, put it in a FIFO, then you generate 225, now it becomes 550, you put it in a FIFO, then again you put 225, it becomes 675, and you consume the first 556, and rest are just sitting there. So this is a simple concept of FIFOs, that whatever you are generating, you keep putting them in a FIFO, and let the FIFO fires the next node once it has enough samples. So you just specify that now you start executing. Okay, so it's So in this operation, you block the read operation, that you don't let the node to read unless you have enough sample for the node to fire. So you put a block on the read. So you're not letting the node to read the FIFO unless you say now you can read it. Okay, but you're continuously writing. Whatever you are generating, you are writing. So this is in Kahn Process Network. You block the read. Okay, don't read, not read. You got to wait. Now read. Okay, but once you are generating, you say you keep writing, because you can't stop that. So this is then once you look at the system level architecture, it will look like this. So there is a FIFO, which is collecting samples, and then you process. And once you process, whatever you generate, you may be feeding to 2 different modules. You put them into FIFOs, and then you kick this, and again you. So that's how once all the inputs have enough data for this node to fire, this node will only fire then, and the fire means it will just execute then. Okay? A simple system level design without you really worrying about how to match up the different data rates, but always you are going to, any interesting architecture you design, always you are going to get into this, that every block would require different number of samples, and there will not be an exact multiple of what the previous block is, usually not an exact multiple of that. As you got to cater, whether it is you are doing it in software, in hardware, you got to worry about that. Okay, so even we would prefer that once you are even generating Python code, you generate them in the same manner. Okay, don't ask Python for example, if you intend to develop an architecture, try to generate your software, the Python, the simulator also in precisely the same architecture that you have for the hardware. Okay, so that is very important. Unless you don't do this, you will not able to do white box testing. You will not able to exactly reuse the same code that you have generated for the Python, for the software implementation in the hardware implementation. So your simulation should mimic the hardware. If you are a hardware designer, okay, it should mimic the hardware, because you got to see, okay, this is how I have imagined I'm going to use Kahn Process Network. These are the processes that I'm going to design. These are the FIFOs. This is the functionality. Then there is a functionality. Then there is a functionality. I don't want this functionality in a single loop. Okay, I want this functionality to be in separate blocks. So you say, this is my first block, this is my second block, this is my third block, this is my fourth block. So you change them into blocks, so that you take this in hardware, you take this in hardware. So you are basically divide and conquer, that your software should precisely look like your hardware. That is the hardware you have in mind. So it's very important that your simulation, because before you design a hardware, you run simulation, it should look like this. For example, this is a JPEG. JPEG is just a video compression algorithm. It's a good example because you have an image, you store an image, it is an RGB, you acquire. DCT works on 8x8 block. Okay, discrete cosine transform works on 8x8 blocks. It'll take an 8x8 block, it'll do the cosine transformation, which is fine. And then quantization. And quantization basically is you take this 8x8 block and then you quantize, you still have the same dimension. But once you do entropy encoding, then it has a very different dimension. Okay, entropy encoding would just, depending upon how much information is there in the JPEG image, it will basically compress. If there's a lot of redundancy, it'll compress more. If it is color, if you take a picture of leaf of a tree, it'll not find too much space to basically do the compression. So if you don't put a hard limit onto how big the size of the image should be, so a lot depends upon the image itself. So here it will be very different, and this is what the sync is, whether you are transmitting or storing or whatever you are doing. But this is the JPEG if you are not really worrying about that to exactly design the architecture. Sometimes this is not a good way to design. Okay, let me also tell you that it's not a good way to design, that you are not really doing all the paperwork before you are getting into a design. You are getting an easy way out, that this is the easiest way out. I don't want to worry about it. I just design a module, put it into a FIFO, kick the next block, to kick the network. And sometimes it may be a good way to design. It again depends that. So, so this is similarly you can do an AMPAG on the same principle of system level design, where at a system level, after every module that has a different character and demands a different hardware. A discrete cosine transform is a very different architecture. A quantization is totally a different architecture. An encoder is totally a different architecture. They are not related to each other, okay? And they must be designed separately, tested separately, and then you are going to connect them together because of the nature of the algorithms that are there to implement all these. So usually the character of those algorithms are very different, okay? So that is why they demand a different architecture. So a lot of limitations of Kahn Process Network way of designing a system level architecture. So it is good, also it is bad. The good is that it's very easy to perceive. What is asan hai, put a block, put 5.4, put block, put 5.4. Once there is enough data, just click and it'll just execute and just generate the results. So it's kind of self-synchronization is happening. So you are not really worrying about, and you only need to make sure that your every block is fast enough to do the requisite processing. But then sometimes you are not reading as first in, first out in many applications. For example, FFT, it's a bit reverse addressing. It's like you read this and then this value, then this value, then this value. So means that typical FIFO operation will not work. You have to copy it somewhere and then you have to run the algorithm. So you are basically another making copy from one memory to another memory, wasting memory, or maybe. So sometimes your data is not precisely FIFO, and convolution requires reading the data again and again and again and again once you are convolving, especially all the CNN networks would require you to have. And sometimes obviously you are resampling, and so sometimes you may want to have even more generic architecture like system on chip. So we call this multi-processor system on chip architecture, okay? And here you say what I'm going to do is I am going to design a processor. Every processor will have its own memory, okay? And then I have a memory controller. This is the memory controller. So processor can read and write in this memory, can also push it onto this buffer where there is a communication controller and a system on chip. So this is network on chip. Now it's a generic architecture. It can say this data should go to this chip or this data should go to this processor. So it's a small internet on a chip. So you have multiple processors, and there is a router. With every processor there is a router, and then there is a network which takes your data from one to any of the chip. So this is also a trend where people say a network on chip. So you put a network on chip, there are routers, there are switches. So this is acting like a switch which gets the data, push it, a small router which will figure out whether it has to be sent to the right or to the left, but it will ultimately reach to this guy, this FIFO, which will use its memory controller to make a copy of the data into the memory. More complex system on chip architecture, and once people say multi-processor system on chip, and then they have other interfaces as well, where the data is coming from outside and it has to go to a certain processor. So there is usually here a DMA or an interface to the PCIX or to other interfaces, and through that. So at system level, you got to figure out that how you want to design. And please remember that a mistake you made here will have very, very serious consequences, because you cannot go back and fix, no, I actually wanted to do KPN, Kahn Process Network. No, you cannot just then change it to, if you cannot handle this type of complexity and then you are stuck and then you say, oh, I want to change my system level architecture, it becomes very difficult. So this design decision has to be very, very conscious design decisions that this is how you're going to design your. For example, this is something which we did earlier. It was a GMSK transmitter and a receiver that we developed for a customer. And I remember the engineer, she was Alina Mufti, who designed this. Actually, this figure is drawn by her as well. And it went in production as well. So it was a telemetry system which could transmit from a flying platform a lot of telemetry data onto ground. And GMSK was kind of a technique that we use for modulation. So if you look, it is a very typical KPN architecture. So we have serial data coming from the interface and a clock. And we collect this, and here is the encryption that we were doing, and we were doing stream encryption. So data is coming, and every byte we encrypt. Okay, so there is a block encryption. For block encryption, you get to collect a block. But usually in these type of applications, you use stream encryption. So encryption is working. It just keeps changing your counter, and then you are just doing the XOR and you send the data. So this is something where the data directly from the interface goes to this FIFO. This FIFO has to collect enough amount of data to kick the forward error correction coding block. Okay, so this is where AES has enough data for this to start its working. So it can use some local memory as well, but once it has processed, it will put data into another FIFO, because a framer requires a different chunk of data, and I'll just put a frame header, and then send it to the next block. So I'll just put that here, and then once it has again a framer will send, and after a framer, every bit has to be modulated. So it is sample by sample. So, and you got to make sure that this never dries, it never looks for data, because now it is actually going to the actual physical interface. So it must have continuous supply of bits so that it is continuously sending the data out. So you got to make sure that it always has something to send, and so the whole thing should be fast enough. Okay? This can wait, this can wait. This is again doing on the, but this framer can wait, or it can process quickly and then it's just waiting for the next chunk to be processed. But it cannot, it has to be in real time to support the real timeness of this interface. So that's how you design, and then you have sample by sample processing. So what we explored was that every serious application that we want to implement would have multiple processors, and then interaction between the processors that may not be that simple to handle, and that's why people go for system on chip or those type of architectures. And so let's do 5 more minutes and then we'll take a break. Yes. Okay, so here is like the options. People can do everything in software, yes, so we are not in this course because of this. People can do things on digital signal processor, yes, but we are not in this course to do this. Then people can design their own instruction set processor. Yes, that is something, an option, where you say, oh, I don't want to deal with these blocks and block going into another block, and so why not, I should have a processor to do this. And this is the case where you want this processor to do different type of things. So you come up with an instruction set and use that instruction set to code the application yourself. Okay? Yes, this is one. And then the best is where you don't want to waste anything, and you say, no, this is, I know this is the application it is going to do for its life. So you do a application specific processor, which is just meant to do the application for which it is designed. A GMSK receiver, a 5G modem, a network processor, which is something like that. So once even the LLM, so for example, a specific LLM that you are doing, a CNN, for example, you say this should just do a convolutional neural network of this complexity. This is the model, and I want to do this in real time with little power dissipation. So again, you are sure that this is the application, but once you are going for a generic, so here you get more flexibility, here you get more efficiency, and definitely cost as well. So here you spend a lot more cost than here, where you're just doing something which is application specific. So it's a lot of trade-offs to decide. And sometimes in many big systems, you have everything. You have a CPU, you have a digital signal processor, you have an application specific instruction set processors, and you have dedicated ASICs. Usually you will find every element of this, because there is part of the application where you use general purpose processor, like user interface, which is code intensive, okay? All the options you want to give to the user, and he is interfacing with the system. Then there's a DSP as well, where you are just doing something which is a code which is not very structured and regular to be implemented in hardware. But then you have an application specific and ASICs as well. So usually a system like your mobile phone will have everything in it. It will have a programmable processor, it will have few ASICs, it will have a digital signal processor as well. So meaningful systems would have every part of this, but this will be a software programmer will be coding this, okay? Maybe an electrical engineer will be doing this, and this is where somebody who understands and doing the architecture, he would be doing this. So different people, that's why a team would have different type of expertise to implement a system like this. So let's take a break, and then we will come to the fully dedicated architecture. Now we are getting inside the block, okay? Inside what happens to a process, inside a processor. And so we'll do that. And तो हम मिलते हैं 5 बजे, ठीक है 5 बजे 5